model, there is anything new to say about the Ising model, well, you'll be surprised. And here we will perform some numerical simulation on the Monte Carlo, on an Ising model, and a very similar one, a Blume-Capel model. And this simulation would explain some experiments. So, great, you know, because for us, the idea is to explain what's happening in real life. And when you have a model that can explain experiment, that sounds pretty good. So yes, the spin models are still useful. Oops. Okay, first let me remind you a little bit of dynamical phase transition. When you have a system, like for example, an Ising model driven by an oscillating field of a period P, okay, what if the system is below the critical temperature, what happens is the magnetization, the response to the magnetization depends strongly on the period of the field. What happens? If the field is very small, it's very fast, so have a very short period, the magnetization cannot switch fast enough to follow the field. And basically what happens is that the magnetization oscillates around one of these zero field equilibrium. So this is the whole order phase. If the driving field is very slow, the magnetization can have the time to switch. And the average magnetization will be zero, and this is disorderly phase. And between these two phases, there is a critical period that defines the phases. So basically, this is the idea. Okay, so here, for example, that's what happened. You know, the green is the oscillating field. In the first one, you see a slow oscillating field. What happened is the black line is the magnetization. Well, the spins have the time to switch around with the field. As the field becomes faster, you see now there is some delay between the magnetization switching, and when the field is very fast, simply the spins cannot complete switch, so they stay switching around the maximum value. So this is the order of phase, because average magnetization is different from zero, and that one is the order of phase. There you have an idea of the hysteresis loops. Okay, well, this is when you know. So the order parameter when you have a kinetic transitions is not the magnetization, it's the average magnetization per cycle of the period is Q. And well, this is the behavior of Q, you know, below a certain critical value of the period, the system is ordered. After that, the system is disordered. And this is a very well-known phase transition that is in the Ising universality class. So the way you detect this phase transition is a strong peak here at the transition point, and of course is size dependent. Okay. So, okay, what you measure in this kind of system, well, suppose that you have a Hamiltonian like that one. So you have in our case, we're interested in a ferromagnetic case, so J will be positive. The spins have to, wants to be parallel to each other, and you have a oscillating field of period P. So you measure the magnetization, the average magnetization per cycle. The order parameter will be the average of the average magnetization, and you measure the fluctuation by the derivative of Q, that is the scale variance. Okay. Well, it is well known that this dynamical phase transition is equivalent to the thermal or temperature-driven phase transition. In the temperature phase transition, the driven is the system driven by the temperature. In the dynamical phase transition, the system is driven by a field of period P, and the order parameter in the thermal phase transition is the magnetization that depends on the temperature. here will be the average order parameter. Okay, this is very well known equivalent between dynamical and thermal phase transition. Now what happened? Let's try some experiment. And a constant bias field. So now your system will be subjected to the periodic chain oscillating magnetic field, but add a bias field, okay? A constant bias field. Of course, in that case, what you do, you break the symmetry, okay? And now you have to define another parameter, is the susceptibility with respect to H field, okay? So let's see what happened. Well, some people did that experimentally. They performed experiment with a uniaxial ferromagnetic seal film, and they found something very, very interesting. It was some completely new result that they have no idea what was the origin. They found that when the system was subjected to an oscillating field of a period larger than PC, that means this is called the supercritical region, that is in the disorder region. So that means a slow field, so the magnetization is able to follow the field. If you add a bias, what happened is something that was very surprising. Instead of one wide unimodal maximum of the susceptibility, I showed you before, now two peaks appear symmetrical about the bias field. At the beginning, they thought, well, probably this result is due to some residual long-range magnetostatic interaction. That's what the first guess. And here, well, don't ask me anything about this experimental part that was performed, by the way, by Riego et al. In Spain, Berger, but basically, when they suggested this very thin film to a oscillating field plus the bias, when they found that they have this, and these are really what it means, they're peaks in the susceptibility. They were really surprised. And they thought, well, there was probably some residual magnetization. After all, the systems are not perfect. Okay, so what we are going to do, we're going to try to understand what's happening in the experiment performing a Monte Carlo simulation of the kinetic Ising model plus a bias. So now we take the Ising model, ferromagnetic Ising model, put oscillating field, period T plus a bias, okay? We perform Clover single spin dynamics in a heat bag at temperature T. We selected the temperature is fixed because we want to be in the disorder region. That's where the experiments indicate that there is a transition. And basically, okay, with Clover, we calculate the change and the probability to accept the change, extending Monte Carlo, okay? There are well-known values, like depending of the magnitude of the oscillating field at certain temperature, the critical P period is well known. Okay, what we got? Oh, we were very happy. What we got was exactly the side bands. When we plot, here is the order parameter, the average magnetization with respect to the bias. Okay, we got this curve. Notice that when the bias is zero, Q is zero, of course, because we are in the supercritical region. We are working with a period, with a slow period, so if there is no bias, the magnetization can follow the field, and the average magnetization is zero, okay? But as soon as we introduce some break that symmetry, okay? So what happened, notice very strange behavior of this. There is one region here for small bias fields that the order parameter behaves almost linearly. And then suddenly it become much more steeper. And these are, of course, the reason of the sidebands. Now, you see when you plot the derivative, basically, the susceptibility with respect to the bias and with respect to the constant, you find two very well-defined peaks. It's exactly what they found on the experiment. So clearly, okay, the sideband, they are not due to any residual magnetization as the experimental stuff. Of course not, because we are obtaining them with the Ising model. There are no long distance magnetization in the Ising model. And here I describe, and notice that the peaks, the position of the peaks is the same for Q and B. I mean, both susceptibilities, the peaks occur at the same point, okay? But the ratio, the height of the peak is different, okay? And one thing is interesting that you see finite size effects are negligible. We went here there, we forgot to say that we're talking square lattices. We went from 64 to 512. We have some results for 1028. We don't see finite size effects that indicate that this is not a phase transition. So,
just quickly, can you just mention again what's the difference between the data on the right, like the big squares and the small squares? Yeah, so like the data that is labeled Q and the data that is labeled B. What's the difference?
Yeah. This is Q is the derivative with respect to the field that give you the fluctuation Q, and this is the derivative with respect to the B. The field B is the field He is the field conjugate to this one. I think I define it here. Okay. This is susceptibility with respect to of the bias. Okay, so wonderful. We got the sidebands. So we found that this is an effect we can reproduce. Clearly, they are not due to remaining long distance magnetization because we got them for the Ising model. They don't seem to be related with the phase transition. You notice that we don't seem to have finite size effects. You know, you increase the size and the peaks didn't go higher and higher. So seeing that this is not a phase transition. Okay, so what is the origin? Why is the behavior of Q changed so abruptly at a certain value of the bias? That's what we want to understand. Now we can reproduce the results. Now let's try to explain them. Well, let's explore the time series of the magnetization. And here, okay, again, we use periodical oscillating field plus a bias. We choose the bias to be positive, okay, and we perform this simulation. This one, I think, is done over two fields, the two sizes, and this supercritical region of the period, and we are basically located almost at the peak for these values. And we plot here how the magnetization behaves for a small system and for a large system. The orange is the oscillating field. Notice that the oscillating field is displaced. It's not centered in zero because the bias is positive. So this oscillating curve is going up. Notice the completely different behavior of the magnetization for the small system and for the large system. In the small system, you see, okay, the total magnetization, eventually the spins try to follow the field. When the field go down, they try to go down. But what happens is that the field switch before they have the time to switch. So basically they go back again and see this process here that the small system have is completely deterministic. So the spins, you notice that sometimes they have the time and they are able to turn. Remember that when the system is in the positive phase, the field is in the positive, is positive, okay? The stable state is the one with the spins up. When the field is negative, the stable state is the one with the spins down, okay? But what happened is that now it's not the same for the spins switching from the positive to the negative than the opposite. Why is that? Because the bias introduced this asymmetry. So it is hard for them, it is harder for them to reach the negative stable state, that we will call that the unfavored one. But here we see that the small system behaves very randomly. Okay, it sometimes it switch. When they switch, it can really, a large amount of, most of them can switch, most of the time they cannot even switch. And look what happened with the large system. With the large system, the behavior is completely different. You notice that this is very deterministic behavior, is the same all the cycles. Here we plot in 5 cycles, okay? Here you see how the systems, behave very deterministic. They flip, they always reach basically almost always the same lower value and the same feeling. That's very strange. A small system, the switching toward the stable phase is stochastic. The switching toward for larger system, toward the stable phase is deterministic and gradual. And say, well, but that's very typical. This kind of behavior is described by the nucleation theory. What happened is this kind of switching that is stochastic is typical for small systems and is due because the way the system switch from one phase to the stable phase is through the growth of a single droplet of the stable phase. This is called in nucleation theory single droplet. When the system is large, the way it goes or decay from this metastable to the stable state is by growing many droplets that they eventually coalesce. I'll show you. So that gives us a clue what's going on here. So let's perform some snapshots of the surface at this point. Okay, because you see this the switching from one behavior to the other is seen just here when the total behavior, the total field is negative. That's what you see, because that is when you have the asymmetry. Okay, so we check in these 2 points when they're the same. Have an image of the surface and look what happened. Exactly what I was talking about. For the small system, here the favorite phase is the field is negative. The stable phase is the one I have the spins down, the red ones. Okay, the green one is the metastable one. And here what happens? When you are here, you see the system is switching through a single droplet of the stable phase that eventually will grow. Okay, it can grow to fill the entire system, so you will have a complete switching, or maybe it only grow a little bit and it will go again. But this is very typical of single droplet. What happened is, for the same values, when you see the large system, you see a completely different picture. Many droplets of the stable phase, remember, is the green one, have nucleated. And this is very typical from, and this defines a deterministic multi-droplet switching. Okay, so now let's analyze this result with the well-known KJMI theory for the decay of metastable phase by nucleation process. As I was telling you, according to this theory, a small system is switching from the favorite to the disfavorite direction. Here I call the negative phase the disfavorite ones, simply because you have a bias that is positive. okay? So the switching for a small system from the favorite to disfavored occurs by stochastic single droplet mechanism. For larger systems, the switching occurs by size-independent deterministic multi-droplet mechanism. Okay? So, and this is related, of course, with the time. The magnetization reversal from, well, the magnetization reversal to plus to minus is only possible when the total field have the opposite sign of the bias, of course. Okay, the bias is positive, you can switch to the negative phase only when the total field is negative. Okay, and the switching to the favored one, to the unfavored one, the up down takes longer than the switch in the opposite direction. And here you see clearly the effects. And here, well, you see we plot 32 and 64. For this smaller system, the switching, you see, is much more random. Okay, sometimes they switch, sometimes they don't. But for the larger system, you start to see, particularly for the 1024, it's a very deterministic. I mean, always go basically to the same value. So, okay, now let's see what happened with the dependence of the critical period. Okay, we plot there the order parameter with respect to the critical period, and here we have the side bands, okay, the susceptibilities. Well, I mean, there is a huge peak at HB equals 0. Okay, we didn't plot because it will make the figure very hard to see. And notice that as P increases, okay, the field, as P increases, the peaks become farther apart. That means that you need harder, stronger biases in order to produce the peak, in order to produce the change in the behavior, okay? And these peaks are becoming, I think, they are flatter. The peaks are becoming slower, okay? We can check this with nucleation theory. There is some long period approximation that say that for very long period, the average behavior basically of the order parameter basically depends on the ratio between the bias, the magnitude of the bias, and the magnitude of the field. And we plot this quantity here, and we see that is the dashed line there, and it fit our result very well. As you increase the period, okay, well, we say that we're increasing the period always starting from the critical point. This phenomenon is only seen for supercritical fields, supercritical periods. And you see that as we increase P in the region for a small HB, our results are in excellent matching with the predicted one, okay? So that's good. Okay, now let's try to quantify a little bit more what's going on. Well, I'm not going to enter in the detail about the KJMA theory, but according to that theory, the nucleation rate for droplet from the favorite to disfavored phase change is with the period of the oscillating field, and the switching time from one type of behavior to the other is of the order of the period. Okay, so using this relation that is well known in nucleation theory, and this is different. Notice that, for example, for the single droplet, the exponents are different. For this multi-droplet, the terms here that depends on the distance of the size L minus A. For the multi-droplet, A is 0. So the switching time is independent on the size in the multi-droplet region, but the single droplet region depends on the size. if we check that, it is evident that we expect that 1/80 minus HV, that will be the maximum possible field, versus log of P must give a straight line with P is large. Okay, and if you take the values there, that A equal 2, B equal 1 single droplet, I equal 0, B equal 2 multiple droplet, the ratio between these straight lines in the single and multi-droplet region must be 3:1. So in order to perform some quantitative analysis, what we did is, okay, we plot the value of the HV at the peak for the different sizes, depending on the period. We got this. Notice that for the small periods, and again, when I say small, I mean near the critical period, but always above the critical period, okay? I mean, this don't go to 0. The lowest value is 256. No, 256 the size. 200 something is the minimum, the critical period. Notice that when P is not very large, the peak doesn't change much with L. Okay, but when you increase the period, the peak change, it increases more slowly. And basically, as you increase the size, the size dependence becomes really disappear, basically. And now from this one, we plot this quantity. This is the quantity that I just said that it must be a straight line for very large P, and you should notice that we found that, for example, for large P, this green dashed line will be, is the one for L32, this one will be for the larger system, 256. We have results more recent for larger system. Well, what happened is we measured the ratio between the slope and we got 2.867, very close to the value of 3 calculated with the nuclear theory. So now we have a more quantitative proof that what's happening here, why these side bands appear, why the Q behaves in this strange way is because simply the system changed the mechanism depending on the bias, the mechanism to switch from one phase to another, change from single droplet to multi-droplet. Here I will show you, and now we say, okay, that's the Ising model. What happened with other models, like for example, the Blume-Capel model? I remind you that this is the basic Hamiltonian for the Blume-Capel model. Okay, that in the Blume-Capel model, now the speeds can take values plus, minus 1, and 0. So this is a much more interesting model because you can simulate system with vacancies. Okay, and this model have been used to create some lattice gas model, to explain some condensation in liquid, binary and ternary fluids. Notice that now you have this term where D is the crystal field. This term, of course, didn't make any sense. Didn't have any role in the Ising model because SI squared is always 1. Here, that term is the one basically that regulates the amount of vacancy. Notice that this crystal field distinguish between the zeros and the plus minus ones. The larger and negative, for the large and negative, the more and more vacancies you have. Okay, the Blume-Capel model have a more complex phase transition than the Ising model. For certain values of D and the temperature in this region, the system have a paramagnetic and a ferromagnetic phase, and this is a continuous phase transition, but the continuous one ended here in a tricritical point, and here the transition is first order. Okay, so we say, well, this model that have more complicated phase diagram will have this same phenomenon with the side bands. Let's see. Okay, again, we know that the kinetic Blume-Capel Ising model, when you suggest the system to oscillating field or PUP, behaves very similar to the Ising model. It have a dynamical phase transition at certain period. If the field is very fast, you have an ordered phase. If the field is slow, you have a disordered phase. The only difference, of course, now the critical period will depend on D, okay? Okay, so we know that, and it is well known that this kind of kinetic Blume-Capel model is in the same universality class as the Ising model. What happens when we add a bias? When we add a bias, will the Blume-Capel model behave in a similar way to the Ising? And the answer is yes. We observe that we have the metamagnetic bands, but now the location, the height of the peaks depend on D. So notice what happened now. This is the Blume-Capel, this is the order parameter, the average magnetization, and these are the He sub Q and He sub B. Clearly we see the bands. Now we plot it for different values of D, okay? Because we're interested to see, okay, it behaves like the Ising model, but what are the difference? The difference will be introduced by the dependence on D because the vacancies. So that's why we change the value of D. And notice what happened that as D is always negative in our simulation, of course, because we want to increase the number of vacancies, and as absolute value D increase, the number of vacancies increase with D negative. And notice that the course at that, what happened, the course becomes smoother. The larger the value of D, the smaller the peaks. So basically, if D is very large, the peaks will disappear, okay? And not only that, but the height, the height, of course, depends, but the peaks, the location of the peaks is, of course, larger and larger values. It's hard to see, but these curves are separating a little bit with this. So the place where the peak is located increases with D. So it is more difficult to make the change for the system when it have more zeros, okay? And again, okay, we explore the system, the magnetization curves, and we pick here. So here, like for example, in the first one, we plot the magnetization versus time for different cycles of the field for different size. When the bias is a strong one, I mean by strong one, the bias is larger than the peak. And notice clearly that for a small system, the behavior is kind of more random. As you increase the size of the system, the behavior becomes much more deterministic. Okay? And here, what happened with the weak, and this is typical for single droplet mechanism. What happens when you have a weak bias? Okay? If the bias is weak, so that means HB is less than the peak. Notice that for all the sizes, including the small one, the behavior is much more deterministic. The spins, basically, most of the case, they will follow the field, and this is typical from multi-droplet, this is typical from single droplet. So we see that again, the side bands are due to this change in the switching mechanism. Here again, a plot. Here is for L64. We plot this size in particular because 64 is small, but is kind of large enough so you can see that there is kind of crossover. I mean, here we plot L equals 64, and you see that for a strong bias, the decay is more like multi-droplet. Remember that we have periodic boundary condition. So basically we have a big one single droplet of the stable phase, that means the negative one growing, and that will be eventually, that's the way the system goes to the stable phase. If you are in the weak bias region, you see a completely different picture. Now you see that they're growing different droplets of the stable phase, okay? What happens is when you see the peaks that change that correspond to this. Okay, what happens is this change here, what is indicated that the system is a crossover between one switching mechanism to another. In this region, weak fields, the mechanism that the system have to follow the field is through the growth of a single droplet. I'm sorry, multi-droplet in this region for weak fields. When the field is stronger, the mechanism is multi-droplet. So this is the origin of this and the origin of the peaks. And again, we want to be more quantitative and try to plot the location of the peak for different sizes. And here we plot again what we expect from nucleation theory. We plot the quantity one between H0 minus HP. For P, for large P's, we expect that this will be a straight line, but the slope of the line will depend on the kind of decay. And again, well, we compare the slope we got for the larger system with the slope we got for the smaller system. And we got 2.406. It's not as good, it's not as close to 3 as it was in the Ising model, but still is very, very good. I mean, remember, this system is different because this system has zeros. But again, that means that the decay is very well described by the nucleation theory. There is some kind of recent results when they calculate some ratio of this slope using mean field, and they got a value much lower than us, okay? So we have very good evidence of what's going on here. Okay, so the conclusions. And remember, it is basically the idea from the beginning is try to see if we can reproduce the bands. Yes, the bands are there. And well, what we got is in agreement with the experiments, our simulation indicate that in both models, the order parameter Q exhibits a strong bias dependence of fluctuation peaks in the susceptibilities, what they experimentally call the metamagnetic bands, and non-zero values HV symmetrical locate around HV0. Well, here, when I say in agreement with the experiments, well, our simulation, I mean, the part that tries to reproduce the experiment is the Ising model, okay? I mean, the experiments physically will correspond more like Ising model than to the Blume-Capel model, okay? We went farther, and what we indicate is that the Blume-Capel model have the same behavior, but there have been no experiments, as far as I know, with something like the Blume-Capel model. And, okay, I think we prove in a very clear way that the experimental results are not due to any residual magnetostatic interactions. And we do not find any indication of hysterectic behavior or diverging finding size effect that would suggest a phase transition. So the side bands are not due to residual magnetization, are not a phase transition. What we found that the fluctuations are associated with a change in the magnetization switching mechanism. What is this change? The change is induced by the asymmetry introduced by the bias field. And we apply nucleation theory and verify that for weak bias or large system, the decay occurs via a deterministic multi-droplet mechanism in this region in the middle. okay, they have the smallest slope, the mechanism, the switching mechanism is multi-droplet. That means that the system starts to switch, creating droplets of the equilibrium phase that eventually they coalesce. And in the region from a strong bias or a small system, that means for the other side, okay, the switching occurs via a stochastic single-droplet mechanism. Okay, the peaks are at the point of fall when the slope changes, and this is the crossover between both mechanisms. What we found also that I forgot to tell in the BC model, some more interesting thing that I forgot to say in the BC model. Okay, single droplet, multi droplet, and this is particularly this size. You say, well, but here is not as clear as before. Then you see the single droplet mechanism. Well, here because of this size, the system really start to show the crossover between the two mechanisms. That's why we wanted to plot that. Notice something interesting. In both regimes, the zero, the black points are zero spins. The zero spins are located at the interface between the droplets. Okay, okay, there's some zero spins around, but basically the interface between the two faces, they're always zero. And this effect, that of course has no equivalent in the Ising model because I have no zeros, suggests that the zero spin act as surfactant, leading to a reduced effective surface tension. We tried to do some calculation, we haven't got any numerical values yet, but it seems that this is what is happening. With that the zero spins act as a surfactant, and it's easy for the clusters to grow with this zero spin in the middle. Okay, so well, basically here that in the Blume-Capel model, and this effect that they become like surfactant, that occurs very close to the tricritical point. Okay, and this indicates that there is some act, the zero field act as a surfactant. Okay, so finally, at the beginning, I say, okay, this is I described to you, this is dynamical phase transition, and this is equivalent to the thermodynamical phase transition. The temperature in one is the equilibrium phase transition is equivalent to the period. The magnetization in the equilibrium phase transition is equivalent to the average magnetization, and they're equivalent. But there are some equivalent, some part there's not. Well, I wasn't totally honest there because it's not true that they're equivalent. When I say they're equivalent, and most people forgot that non-equilibrium and equilibrium phase transition, when they're equivalent, is near the critical point. If you go outside this region, equilibrium and non-equilibrium system can behave in a completely different way. And the non-equilibrium system have a much richer behavior. Like, for example, in this case, you say, okay, yeah, these are equivalent here. Wait a minute, they're equivalent near the critical point. As soon as you go outside the critical point, new effects appear in the non-equilibrium system, as here that they appear the metamagnetic bands. Okay, and well, we say that this kind of study can be important. Well, first, it's always nice that you have an experiment and you can explain this experiment theoretically, okay? And this can be important for design of devices that involves magnetization reversal switching, memory element switches and actuators. Well, this job has been done in collaboration with Riego, that you all know very well, who's here, and with an undergraduate student of mine, Celeste. So, Thank you very much for your attention.